Okay, I think we can start. Hello, everybody. A few more people might join, but I think we can just get going. So welcome to another seminar as part of VTSS. It's good to see that there's by now an established community of people that come every week. And let me thank Sophocles, first of all, for accepting our invitation. It's great to have you. And Dennis for accepting to be our panelist or informal discussant. It's great to have you. So the rules of the game are the usual. We are recording, and Sophocles is happy to take clarification questions during the talk. And then when we stop the recording, we can open to Q&A and have a more informal chat. If you have any question or clarification question, just unmute and go ahead. Otherwise, if you can kind of remember to keep your microphone muted to avoid any disruption. Ideally, you do not pose questions via the chat. But if you have any technical problem and you cannot ask questions otherwise, feel free to use the chat and we'll read it for Sophocles. And thanks also to the very many who submitted a paper for our workshop, which is scheduled to take place on April the 20th, I think. We'll soon get back to everybody and put together the program. So that's not ready yet, and more information soon. So I would say that's it on my side. Sophocles, it's on you, and we'll try and remind you a bit closer to the time before an hour is passed.
Well, thank you, Michele. It's a great pleasure to present in this virtual time seminar series. And I'm going to talk about cointegration with occasionally binding constraints. This is joint work with my colleague, James Duffy, who is the big intellectual force behind this paper. And our former student, Sam Wycherley, who was an undergraduate here, and then he did a pre-doc RA with me before going to Stanford to do a PhD, so he's currently at Stanford. So let me first start by giving a little bit of motivation for this work. It may have been a while since you heard the word cointegration. It's not one of the most popular topics these days, but looking at pictures like that, you will realize why we want to resurrect it. So I plotted here a couple of time series, which are policy rates from the US and the UK, the federal funds rate on the left and the UK overnight interbank rate, which are used as a main instrument of monetary policy in these countries. And just by looking at those time series, we see, well, on the one hand, that they exhibit wandering behavior, which is akin to stochastic trends. But also we see that they spend quite long periods of time near or at zero, which is the usual zero lower bound problem. So the stochastic trend part of those series has been a topic in time series analysis for several decades. It's well understood, and there are linear models of unit roots and cointegration that analyze this kind of series. But the combination of this together with occasionally binding constraints is something that hasn't been done before. And that's what we wanted to study in this paper. Can we model series like that, like these, with something akin to vector autoregression, which is the typical tool that we use for time series, economic time series. And the background, the model that we started working with, is a model that I studied in a recent paper in 2021, which is a VAR, but a VAR that contains a variable subject to an occasionally binding constraint. And that variable may be partially observed, hence, so the data may be censored, but also the constraint may change the behavior of the entire vector of time series across regimes. So when the variable is constrained or not, which I call the kinked. Hence, I came up with the terminology censored and kinked structural vector autoregression, which we will use in this paper, the CKS-VAR model. And the CKS-VAR model, you will see here, represented in terms of two sets of variables. There's a variable y, which is subject, which is causing the dynamics to change depending on its sign, whether it is above a threshold or below. And there's a vector of variables x, which are unconstrained. And their level does not change the dynamics. and there is the y enters non-linearly in the model, both contemporaneously and in the dynamics. Now, this is a system of piecewise linear equations, which we can write in structural form. So it could be a structural model of the economy, and I will talk about examples later. So the first thing that we need to understand is that this model may not have a unique or any solution for all possible values of u. And so what I did in that paper was one of the things that I did is I derived conditions for existence and uniqueness of the solution, which are called coherency conditions in the earlier micro literature. And that's basically that the sign of the determinant of the contemporaneous impact matrix should be the same across regimes. So either both positive or negative. And the point of that paper there was to argue that the kink, possible change in the dynamics across regimes, generates useful information to identify causal effects, in particular the causal effects of monetary policy, the variable subject of the kink. Now, another recent paper by Aruba, Mlikota, Sophocles, and Villalbazo also looked at VAR with occasionally binding constraints. They started with a model that looked a bit more general than this, but then once they imposed the conditions for existence and uniqueness, they got basically the CQ as well. So it suffices to study the current literature on VAR with occasionally binding constraints. So in both of those papers, both my paper and the Aruba paper, the main motivation and interpretation of the model was coming through monetary policy, where YT plus is the observed policy rate, which is only observed when it's above 0. And YT minus was called the shadow rate, which represents the desired stance of unconventional monetary policy, like when the conventional policy instrument is constructed. I'm going to use this example throughout this presentation. The important thing to understand is that for the purposes of this talk and for this paper, it is irrelevant whether YT minus is observed or not. Right? So what matters is whether the dynamics change across the threshold. And we can think of applications, for instance, on fiscal policy. I am currently working on one where we can think of the Maastricht Treaty criteria, whether you exceed the 3% deficit threshold, whether the behavior of the economy changes or not. That would be an example of YT being observed both above and below the threshold. The leading application on interest rates is one in which the shadow rate is not observed, but that's not relevant for the analysis of the dynamics. Let me briefly pause in case there are any questions. Okay, let me move on then. So I will go straight to this illustrative macro example, which I will use throughout. So this is a stylized macro model for monetary policy, which I managed to write down into two equations. Typically, the stylized monetary policy model has three equations, one for inflation, one for unemployment or output gap, and one for the policy rate. But if you combine the two equations governing the transmission mechanism, the IS and the Phillips curve, then you can get a single equation for inflation, where inflation, in deviation from some target, may have some intrinsic persistence due to backward-looking behavior, some kind here, driven by this condition. But importantly, it reacts to movements in the policy rate, IT, and it may react, so the coefficient theta is typically negative, so when you raise interest rates, inflation goes down. But it may react differently depending on whether the policy instrument is above or below the threshold. And this parameter here, mu, which I introduced in my earlier paper, can be thought of as measuring the effectiveness of unconventional monetary policy in this application. If IT minus represents the shadow rate, the stance of unconventional monetary policy, well, if mu is equal to 1, conventional and unconventional policies are the same, they have the same effectiveness. If mu is less than 1, unconventional policy is less effective. Right? So that's one example that we will use throughout. And there's another variable here, RT star. RT star is the real natural rate of interest, and the shock epsilon t, which is like a combined demand and supply shock. And on the policy side, there's a usual Taylor rule, which says the nominal interest rate is deviates from the natural nominal interest rate, which is the natural real rate plus the inflation target, whenever inflation deviates from target. So it reacts to deviations of inflation from target. The coefficient gamma typically greater than 1. Now, the micro foundations for this model can be found in some earlier paper of mine. Ikeda found here. So you can motivate it through a New Keynesian dynamic stochastic general equilibrium model with a particular model for forming expectations. And you get an equation like this, or to a system like this. So in those papers, in my earlier paper, and in the paper with Ikeda et al., we focused on the empirical implications of this model in under stationarity, so the short-run dynamics implied by this model, and we exploited the variation in the short-run dynamics across the threshold for identification of the causal effects. But we may like to account for stochastic trends in this model, not only because of what you saw in the very first slide, when you looked at data on interest rates, that they don't look stationary, but also because there may be theoretical reasons to expect stochastic trends in this model. And I'm going to mention two here, which were the original motivation for this paper. This paper emerged out of discussions between me and James about what would happen when we allow for these kinds of trending processes in the model. So in the canonical model that I studied before, I had treated the natural rate and the inflation targets as constants, but there is a literature on the natural rate that allows it to drift. There's a stochastic trend. In fact, there's a very seminal paper by Laubach and Williams, where they treat the natural rate of interest as a random walk, and they extract that estimates of that natural rate using a Kalman filter in a linear state space model, and they publish it in the New York Fed. So they publish it in real time, and it's used. It's looked at both by policymakers and by investment bankers, because it is a useful indicator of the monetary policy stance. If the nominal interest rates are above the natural rate, then policy is contractionary, they are below its expansion. So this is something which is of interest, and it has some sort of foundation in the macro literature. So a stochastic trend coming from the variation in the natural rate of interest, the equilibrium rate of interest. Another literature allowed for variation in the inflation target. So allowing the target or long horizon inflation expectations to drift also in stochastic way, so following a stochastic trend. So now, in either of those two cases, we can replace any model we use to close the system for RT star or pi bar. We can put it into this model and express the variables pi t, the observed variables pi t and it in CKS bar form. And as I mentioned earlier, the relative effectiveness of unconventional policy in this model is measured by me. Now, at the risk of belaboring the point a little bit, I will just show you how you can go from this model here with a model for those two variables into a CKS bar model of this form. Right? So we start with the original two equations that we had before. Let us assume, for instance, that the inflation target is 0. So we take it out of the model. And let us assume that the natural rate formula is an AR1, an exogenous AR1. If you substitute this back into the system, then you get a piecewise linear structural vector regression. It can be written like this, where the coefficients of the dynamics and even the contemporaneous coefficients change depending on whether the interest rate is above or below the threshold. Right? Questions? Okay, let me move to our contribution. So what does this paper do? What did we set out to do? Well, the very first thing we asked was, under what conditions can a CKS bar model generate data that is stationary, ergodic, which is what I had used in my earlier paper as a high-level assumption in order to justify doing inference in this model under stationarity. And it turns out that this is not trivial. And it's not trivial because this nonlinearity doesn't allow us to infer the stability properties of the model simply by looking at the characteristic roots of the polynomial on the positive or the negative side, right? What we have to do is we have to trace out the dynamic path of the model for all possible regime switches at any point from any initial condition, and that is difficult. It's infeasible computationally, but there are bounds that we can provide. There are bounds on the joint spectral radius of the system, and so that's what we do. We derive bounds based on the literature on threshold for regressions, and we can exploit the structure of this model, the fact that the lags can only move across regimes in a particular way, right? So we can avoid certain regime transitions to make more efficient computations of the less conservative estimates of the joint spectral radius in order to get sufficient conditions for stationarity and ergodicity of this model. And we are currently in the process of providing programs for users to implement. But this presentation is not going to be about that. It's not going to be about the conditions for stability. It's going to be about how to characterize the behavior of the data, the long-run properties of the data when there are unit roots, and what kind of cointegration can arise from this model. So that's what I'm going to focus on exclusively today. Right? And that's important, both because of the implication that I used to motivate what I'm doing, and also because it allows us to confront a broader problem and enables us to give an answer, possible answer to a question that has eluded answering for a long time. Right. So what is the broader? Yeah.
Just quick curiosity. Why restrict phi x to be the same? Not in terms of the sign of x, because interest rate is not in x, but like you see, we're going depending on the sign of y first.
So the restriction that phi of x needs to be the same is necessary for coherency. Right? We need to avoid jumps, and this is in fact the thing that I mentioned. Aruba and Sophocles and Aruba, this paper that started from a more general model and then imposed restrictions for coherency. The restriction that they imposed, they discovered, which is kind of intuitive once you think about it, is that the model is continuous at the kinks. If we allow phi x to change sign with the y, so then it's like allowing for jumps. So if you think of this as a system of piecewise linear functions, for existence of an equilibrium, these functions piecewise linear functions must intersect at one point. In fact, they must intersect uniquely. If there are jumps, then it's no longer possible to guarantee that there would be an equilibrium.
Okay, too much of which change. Okay.
Right.
Okay, thanks.
All right. So what is the broader contribution? The broader contribution is an answer to the question, how can a non-linear vector autoregression generate genuinely non-linear cointegration? And even though there's a huge literature on non-linear cointegration, the answer to that particular problem has remained elusive. In fact, there's a very nice review article by Zostheim a couple of years ago, where he basically makes that exact point. He says, we would like to start from a VAR, primitive VAR, and derive non-stationarity and cointegration from it rather than impose it in a vector error correction. But nobody has done it. There's a slight exception to that. There's a type of model that Zostheim and co-authors proposed in JPS in 2017, which allows for threshold cointegration, but it's too restrictive to cover the setup that we want here. So it allows for, it's a VAR with the regime switching, but the threshold depends on whether the lags of the variables live in a compact subset. But here we want to allow for open subsets and compact subsets, so positive and negative. And it's also only for VAR1. So we provide more general results. So what do we mean by nonlinear cointegration? We mean by processes that share a common nonlinear stochastic trend or nonlinear stochastic trends. And we also want to allow for cointegration to differ across regimes, either the cointegrating rank to differ across regimes, or if the cointegrating rank is the same, the cointegrating relationship to be genuinely nonlinear, to differ across regimes with the state of the economy. And we want this nonlinearity to be in terms of the levels of the variables to match things like the interest rate application here, not in terms of stationary combinations of the variables, which is what the literature has already done. And it turns out, even though we didn't set out to solve that problem, we set out with a very narrow objective to understand what happens to the CKS bar when there are stochastic trends. It turns out that the CKS bar offers us sufficient flexibility to get useful departures from linear cointegration, interesting departures, and at the same time, it's sufficiently tractable for us to be able to fully characterize its long-run properties. So it's a happy coincidence, if you like. And we believe that we're the first to do that. Right. So let's go back to the model. And okay, motivation. Why do we consider unit roots? I've already given some specific motivation in the context of the application of the interest rates, but more generally, we prefer VARs in levels. It's a general statement in macro because, for various reasons, differences can remove long-run information, which may be useful for forecasting. Non-linearity may depend on the level of YT, so we can't difference the series to stationarity necessarily. And in the canonical application that we consider the policy rate, inflation, and employment, the stationarity assumption seems rather heroic, even though I managed to get away with it in my previous papers. So another reason and motivation for me, given my interest on identification of structural models, is that by studying stochastic trends, we can use the long-run properties of the data and changes in the long-run properties of the data across regimes in order to help us identify causal effects or structural parameters of interest. In particular, we will see how we can use this theory here to make inferences about the long-run effectiveness of monetary policy through changes in the long-run behavior of the data across regimes. Right? And I will make that very precise in the conclusion. So this is why we consider the approach. So in the rest of the talk, I'm going to give a primer on linear cointegration. I know you've all at some point studied Johansson, but it may have been a long time. So it would be useful, and then I'm going to move to nonlinear cointegration, basically as well. So in a linear VAR of dimension P, of order K, right, we can write this in terms of a matrix-like polynomial phi of L. So phi of L applied to ZT, a vector of dimension P, is equal to UT, where UT is an ideal process, and we can represent this in vector error correction form as the change in ZT is equal to pi, the long-run matrix, ZT minus 1 plus the sum of matrices. This is all familiar to everybody. And then the usual assumptions that we make in order to get into cointegrated VAR is that the matrix-like polynomial has Q unit roots, Q less than or equal to P, and the long-run impact matrix pi has rank R, which is P minus Q, and R is the cointegrating rank of the system. Right? What are the consequences of this? As we know, we can write pi as an outer product of a matrix alpha of dimension P by R and a matrix beta transpose, where beta is again of dimension P by R, and beta represent a basis for the cointegrating space, right? Such that R linear combinations of the original data, beta transpose Z, called psi t, are stationary, and we call them the equilibrium average. Deviations of psi from 0 will vanish asymptotically in the long run, right? And the limiting process generated by this model for the levels of ZT, appropriately scaled by square root n, can be represented as a linear value. Right? So this is a model of linear stochastic trends and linear cointegration. Now let's see how these things can be generalized to, before we go there, just a visual inspection of a cointegrated system, bivariate system. So we have two variables, y and x. The, as I said, the scaled vector y and x converges here to this linear Brownian motion process, which is one-dimensional. Why? Because this is a cointegrated system. So it is I1 with a single cointegrating relationship, and the cointegrating vector is -1, 1. The line, the blue line here, represents the kernel of the long run. In fact, it represents the orthogonal complement of beta. And if you like, it is the space of steady states of the system, stochastic steady states, where the system will be in the long run, because all deviations from the blue line will vanish. And if you look at a plot of the two series, they tend to wander, but they wander very closely to each other. Right? So that's a standard linear cointegrated PAL. Now let's see what happens when we go to the CKS. Well, first, let's note that the CKS var, in terms of dynamics, the CKS var for the K, strictly speaking, has 2 to the power K different regimes. And these regimes are determined by the sign of the little variable y and its first K lags. It here, it's in canonical form, so the first K lags. But in fact, if there are stochastic trends in this model, the system, or the variable y, will spend very little time around 0. So most of the time, it will either be completely positive, all the y's, all the k lags will be positive, or they will all be negative. So it suffices to consider only 2 regimes, not 2 to the power k regimes. One regime where the first k lags are all positive, and another regime where the first k lags are all negative. So in fact, it suffices to work with 2 lag polynomials, the positive lag polynomial and the negative lag polynomial, when we want to characterize the long-run properties of the series under stochastic trends. Right? That's the first insight. So let's use that. Next, we can look at the counterpart to the linear cointegration VAR assumptions for this CKS form. And we have to now consider the characteristic roots of 2 characteristic polynomials, the positive and the negative one. And let's call Q plus the number of unit roots for the phi plus polynomial, and Q minus the number of unit roots in the phi minus polynomial, the negative side. And similarly, define R plus and R minus as the rank of the long-run matrix for the positive and the negative regimes. Right? Now, Q and R may differ across the positive and negative regimes. So the question is, what will happen to the level of the series appropriately scaled? Right, asymptotically. What will they converge to? Will they converge to anything meaningful? That's what we derive. Okay. Right. So let's rewrite this model in a vector error correction form. Right. So we will have the change in y and the change in x. Now it will depend on two. Sorry about that. Sorry. So what was it here? So notice that the coefficients here on the long run impact matrix may differ across regimes, and also the coefficients on the lines may differ across regimes. And if there are stochastic trends here in this model, there will be reduced ranks here. Then Z, the rescaled levels of the process, will concentrate in steady state in two different sets. One is defined by the kernel of pi plus of the impact matrix for the positive side, so this with that, and the other one concentrates on this, the pi minus. Right. So now the set of steady states is no longer a linear subspace. It is piecewise linear subspace. So Z, the rescaled process, must be a nonlinear function of the partial sums of the errors, unlike in the linear model. The question is, what function is it? And here we discovered that there are three possibilities, right? And this is the new results in the paper, right? So one possibility, which we called regulated cointegration, is when the rank of the pi matrix changes across regimes. And notice that the rank of pi, the pi plus and pi minus, can only differ by one. Why? Because pi plus and pi minus only differ by one column. Right? And so without loss of generality, here we say, let's call R plus equal to R, and then R minus equal to R plus 1. Because if we wanted the opposite, we could just change the sign. Right? So we will always say the negative regime under case 1 will have rank 1 plus the positive regime. So one fewer unit. So the negative regime is more stationary than the positive. Right. Now, in that case, Y will turn out to be something called a regulated Brownian motion. And if some of you, like me, haven't seen the word regulated Brownian motion before this paper, I'm going to show you later what it is. It's an old concept. The second type, so in terms of the first type, there is some prior literature on it in the case of a univariate model. So obviously, a CKS-bar is a generalization of a univariate model where there are no x's. And for a special case of this model here without the x's, these results on regulated Brownian motion have already been defined, derived in the past. So we generalize them a little bit here, and we generalize them in the vector case. But what is entirely new is this notion of kinked cointegration, which is case 2. Now, the cointegrating rank is the same in both regimes, but the cointegrating vector changes. So we can see meaningful deviations from linear cointegration because it changes in a regime dependent, in a non-linear way. And the result would be something we call kinked Brownian motion. Again, non-linear, piecewise linear. And the final case, case 3, is where we have linear cointegration. Why? Because the y, the little y, is actually stationary. And all the unit roots come from the x. And that, in fact, is already studied in the literature, more generally than in our paper. We're able to offer some more, some new results even in that part of the literature, just because we have more structure than the previous papers when we look at the linear cointegration. All right. So let me talk about the regulated cointegration first. Let me see any questions. Okay. So for this, it would be useful, and I'm glad that Anna is here in case I I get a difficult question, it would be useful to refer to results in a paper by Anna and James on the univariate dynamic topic model. What is the univariate dynamic topic model? It's an autoregressive model where we observed a limited dependent variable. It's not negative, but also not only the variables are negative, but all the lags that enter the dynamics are the lags of the observed non-negative variable. Right, so it's the positive side. So if you think in terms of the general CKS bar, that's a special case of that model where the phi minus polynomial is equal to 1. If you were thinking in terms of interest rates and you were thinking of an autoregressive univariate autoregressive model of the interest rates, there would be no shadow rates in the dynamics, which turns out to be the model that Aruba et al. They mentioned in the introduction. We didn't have shadow rates in the lags. Now, YT plus, if the phi plus polynomial has a unit root, YT plus will wander randomly above 0 like a random walk, but YT minus would be like a stationary process, because as soon as you pass the threshold below 0, there's no more feedback from the past. There are no dynamics, right? So the process YT will spend, and YT, remember, it's the positive and the negative side, right? We'll spend very little time below 0. Most of its time will be above 0, if there's a stochastic and above 0. So in terms of the long-run behavior of the process, only Y plus will contribute, because Y minus will be a vanishing fraction of the sample. And so the limiting behavior of this process will be something called regulated Brownian motion. I believe the term was first derived by Giuseppe in a very nice paper in 2005. So this is a linear Brownian motion where you add back the worst case negative value from the past, right? So it's basically like a random move that is constantly reinitialized whenever it tries to get negative. Okay, so let's see how it looks like, because I have never seen anything like that before. So this is here in blue, the linear Brownian motion. And these are just simulations. All the curves that are given here are based on the same underlying process. This is the regulated Brownian motion derived from this. So if you notice, it's always positive, and it's a bit higher than that. So this is always bit high. And of course, these two series are materially different. So if we observed data having this behavior, right, we can distinguish it from a model that expects this. And this is what we can use in order to identify structural parameters from long-run information. Now, another type of process that features in the three cases is something called the censored Brownian motion, which is basically only the positive side of this. Right, so it's above the red line. And the kinked, which is the V, and I plot the V together with the W. Here, the V has a different scale above and below 0. So it's the same underlying stochastic trend that drives everything. But when things are positive, the scale is much higher than when they're negative, when the W is negative. Right? So let's look at what regulated cointegration looks like. And let's consider the case where we have two variables, y and x as before. And remember, for regulated cointegration, we have a change in the cointegrating rank. So above 0, we have rank 1, exactly as in the linear cointegration case. Here. But below 0, we have rank 2. So it's stationary. So if we think about the space of steady states, well, it's going to be the point, the origin for the negative side, and this half line for the positive side. And if you look at how the process behaves, it spends very little time below 0. Exactly like the regulated Brownian motion that I showed before. how does this square with the macro example that we used in the motivation at the beginning? Well, take our stylized, transmission mechanism Taylor rule. Let's kill the natural rate. Let's assume that the natural rate is constant, so normalize it to 0. But let's allow the inflation target to drift. And we're going to allow it to drift, but also have this little delta here, which is negative. So it allows for adjustments to the trend, to the target or trend inflation, reacting to deviations of actual inflation from the target. Right? Now, when interest rates are positive, you can work through the algebra and find that monetary policy will be fully effective in stabilizing inflation. So when it does its magic, inflation will be equal to the target plus a white noise, which comes from this demand supply shock. Right? So monetary policy is very good at stabilizing inflation around the target. And of course, the interest rate would be close to the inflation target, but then the inflation target will drift. So now the inflation target is I1. We see a stochastic trend simply because policymakers are changing the target. That's when IT is positive. When IT is negative, if monetary policy is not fully effective, now inflation will not hit the target. And in fact, when these things are negative, inflation will stay below the target. And that will cause the inflation target to be adjusted upwards. And so inflation target will become stationary and the whole system will become stationary. And the process will spend very little time below zero. So that is how we can get a model like that with some sort of macro foundations, kind of macroeconomic model in the background. Now, whether this is realistic, let's say a realistic description of recent monetary policy and monetary history, I'm not sure, because the process obviously spent a lot more time at zero. Interest rates spend a lot more time at zero than you would expect with this model here. So I find case 2 kink cointegration a bit more realistic for at least the application that we have in mind. So here's an example of kink cointegration where you have cointegrating rank 1 both above and below, but the cointegrating vector changes. Right? And till it's below 0. And another example, even more extreme example that I will give you with a macro illustration, we have y and x cointegrate above 0. You see them moving together. But when y is negative, it remains non-stationary, it's trending, but x is stationary. Right? So the behavior changes. In a non-trivial way. So let me give you this example of kink integration. Again, the illustrative macro example as before, but now let's kill the target, the variation in the target inflation, so the trend inflation, normalize it to 0, and make the natural rate of interest around it, like in the Laubau and Williams paper that I mentioned at the beginning. Now we can write the system like this, it's a bit leaner, and we can see what it looks like, what the dynamics look like under the 2 different regimes. The conventional policy regime, again, things work like a charm, inflation is stabilized, it becomes white noise around the target of 0, so it's stationary, but the nominal interest rate, which has to follow the natural rate of interest, inherits the stochastic trend in the natural rate of interest, so it's I1. So cointegrating rank is 1, but the cointegrating vector here gives a 0 to I and 1 to I. Okay? Like this part here, it's coming. The sign is flipped. I wish I had written it the other way. What happens with unconventional policy? Well, with unconventional policy, if it's not fully effective, it cannot stabilize inflation around the 0 target. So now inflation will get some feedback from the natural rate, which is drifting. So both inflation and the nominal rate below 0 will inherit the stochastic trend from R star, and they will be integrated. But of course, they are co-integrated with a cointegrating vector, right, given by this, right? This minus that. Okay. So if mu is different from 1, there will be a change in the cointegrating vector across regimes. But this is only if mu is less than 1. If mu is equal to 1, this becomes 0, right? And so we get back to this, right? So there will be a change in the cointegrating vector, cointegrating space across regimes, if and only if unconventional policy is not fully effective. And so we can use that and identify the long-run properties of the series, and we observe such change. Then from the lenses of that particular model, we can infer something about the effectiveness of unconventional policy. Right, so I'm doing very well in terms of time. I'm going to finish a bit early. We can have plenty of time for discussion. So just to summarize, for the remaining paper, the contribution is to prove a version of the Granger-Johansson representation theorem for the CKS value. So we want to obtain a nonlinear VAR representation of the equilibrium errors. The equilibrium errors will be functions of the original data that will depend on the level of the variable y. So when y is positive, there will be a different vector than when y is negative, in principle. That's case 2. Or in case 1, well, again, it will be different because the whole rank will change. But the difficulty there, which is non-trivial, is unlike the linear case. In the linear case, the linear VAR, once you find the beta, it's trivial to show that it's going to be stationary. But here, the stability properties of the model, because of the nonlinearity, are not trivial to derive. So we need to be very careful about controlling the evolution of the stationary errors, well, candidate equilibrium errors here, exciting. And we do that using those bounds on the joint spectral radius that we derived in the first part of the paper that I didn't talk about. Okay. And so we have some high-level assumptions there. And we characterize, as I've already shown, illustrated before, the behavior of the levels, the rescaled levels of the series, using new limit theorems. For convergence to kinked, as well as regulated, we are generalizing a little bit also these results, but mainly this is the result of kinked processes. So this is just representation theory. We have not worked out any estimation results. So this is the first step. But we believe these results are foundation for an asymptotic likelihood-based inference in this setting, which we are currently working on. That's what we want to do next. And of course, even though we derived everything in the context of a scalar y, so only one threshold constraint, so one nonlinearity, we can generalize multiple nonlinearities or multiple variables.
Can I just clarify? So the in the Engel and Granger representation, there is a condition for the variables to be at most I1 and not I2.
Yes.
Thank you. Yes,
exactly. So our results are exhaustive only for the case of at most I1. Well, we have to generalize a little bit our definition of what I1 means here, because we don't have exactly the same, so, because we don't have difference. We can't difference things to stationarity. So, but yes, we have variables at most. So we have not looked at I2. So that's another extension that is interesting.
But are you able to provide like the so in the Johansson setting, there's a matrix that needs to be invertible. Is there a similar matrix in your setting that needs to be invertible, or what's the analog? Well,
the analog is those exactly. That's not a matrix that needs to be invertible. We have to control. There's a companion matrix which differs across regimes, and we can write, if you like, a VAR representation for these equilibrium errors and the variables and their first differences, and that will be regime dependent. And we want to bound the joint spectral radius of that companion.
I see.
And that's how we get the conditions, the sufficient conditions for the process to be unstable.
I see.
Thank you.
Thank you. Thanks.
Right, so it's not entirely true. Okay. Right. So let me wrap up, and then I'll give the floor to Dennis to grill me. So what we do here, well, we analyze the CKS-VAR model that provides a structural way to model series with threshold type nonlinearities. This is a type of endogenous regime switching that occurs due to occasionally binding constraints. But it can be generalized to other contexts. And in this setting, we provide sufficient and verifiable conditions for stationarity and periodicity. And we have a complete characterization of Unit-Knudsen cointegration up to the caveat that Majid mentioned, that we only have up to I1, no I2. Right, so up to I1, it's a complete characterization. And we think that is useful for the literature on nonlinear cointegration because it provides an answer to the question that Schotstein raised: how can we go from a nonlinear VAR to nonlinear cointegration? This gives us an answer. And on the inference side, where the threshold type nonlinearities in the long run can provide useful information in macro applications to identify or test questions of policy interest, such as the effectiveness of unconventional policy. Right. And now we're working on maximum likelihood based inference in the constant run case, case 2 that I mentioned. That's what we're currently doing. Thank you very much.
Thanks for the thoughts, Sophocles. Let me stop the recording.